All right, well, let's get into it. Hi, folks. I'm Ruben Bond. I'm a principal engineer on the Orleans team at Microsoft. You can see my Twitter handle down there, at Ruben Bond. And I want to talk to you all about Orleans, and in particular, how we're using it to build production services at Microsoft. So we won't cover too much detail about Orleans itself as a framework, but I want to give you a very brief overview for the folks who are not really familiar with it yet, or people who want a refresher. So Orleans is a framework for building distributed applications, and in particular for building scalable, fault-tolerant applications that are composed of distributed objects that we call grains. And by building your applications using these grains, you can run your code on a single server or on a large cluster of machines without needing to change your code. And Orleans helps with a lot of the heavy lifting. So things like forming into a cluster, distributing load across the cluster, letting these grains communicate, and recovering from host failures. And that might be things like when you're scaling out or scaling in, doing rolling upgrades, or even just traditional host failures when a machine goes down. Now, Orleans really shines when it comes to writing stateful services. So that can be tricky to get right otherwise, especially in a cloud environment where those machines are coming and going frequently. The final thing is Orleans is battle tested. We've been running it in production for 8 years now. I mentioned grains. Grains are the building block of any Orleans application, just like how a control is a building block of an MVC app. And grains are brought into memory when they're needed, and they're removed when they're not in use anymore. If a host in the cluster fails, Orleans will detect that, and any grains that were on that failed host, well, they'll be reactivated somewhere else the next time that they're needed. So as a programmer, you don't need to worry about where a grain is activated in your cluster, or if it's activated at all, or if you've ever even called it at all. You simply make calls to your grains and Orleans will figure out the rest. That's the beauty of it in a nutshell. Now, conceptually, a grain is a distributed object composed of these three things: the identity, behavior, and state. The identity is this type plus a user-defined key. So you see the type there is user, and the key is a string Ruben. Now, the behavior is a .NET class and a communication interface. We have user and IUser here. The state can be in-memory state. That might just be properties on your class, or it could be persisted state that gets injected into the constructor of the grain. And we'll see that on the next slide. So this is the only code-heavy slide in the presentation, and that was really kind of conceptual and way before. But to look at how it looks concretely, here's a grain that we've defined. So we've got IUser, this communication interface up top, and you can see that it has two methods there: send message and get messages. Now, I want you to notice that they're both returning tasks. And the reason for that is that, well, these are distributed objects. So they could be, when you're making a call to one of these things, it could be on a totally different machine to where you're calling it from. And so because that might involve I/O, these things are naturally asynchronous. Now, below that, you've got user, this user grain, which implements that interface. So see how the constructor has this parameter that gets injected, and that contains a state. In the top right there, you can see how we get a grain reference and how we pass in the user, IUser type, and also Ruben, that's the name of this grain. And then below that, how we call them. So we do this asynchronous RPC approach. So you await a call to this grain by reference, and you can also get results back from that. So one more thing that I want you to notice there, look at that send message method down there. It's a simple kind of implementation. We're just adding a message into a list and then writing some state. But notice how we don't have a lock around that. There's no concurrency control here. And that type that we're adding that message to, that's just a list of messages. So it's not thread safe by itself. And the thing to note there is that Orleans, by default, is going to make sure that only one call is executed at a time for a given grain. So for the Ruben grain, for example, it's only going to execute, say, send message, or it's going to execute get messages. It's never going to interleave these things over each other. And that means you don't have to write potentially buggy concurrency safe code because it's safe automatically. And so you avoid a lot of concurrency issues by doing that. Another thing to notice here, we have write state async. But if you look, there's no read state async, there's no load state async anywhere. And the reason for that is that these things are stateful objects. So we can load state once before the grain user code ever gets executed, and we keep that state around in memory all the time while the grain is active. And so you can serve requests straight out of that in-memory kind of cached state, and you only need to hit the database when you're writing the changes back to the database, right? So the nice thing there is you improve latency. You don't have to hit the database on every request, so you skip that bit. And you also reduce load on the database. So it's not much nicer there. All right, one last thing about the framework. I just wanted to highlight a few of the things here. Now you saw that nice and simple, maybe even simplistic kind of persistence on the previous slide. And we were dealing with .NET objects and we had this write state method, very abstracted away from the database. Now that doesn't work for everyone. So a lot of teams around Microsoft, for example, they're just going to write directly to the database. They might interact with SQL or with, say, storage or Cosmos, and they can do that directly. There's a couple reasons why they might want to do that. One of them is that they might want to have a lot of control over the shape of the data. So they want to be precise about how it's stored. Another reason could be that they want to take more advantage of the particular database's features. Let's say you want to use queries or indexes or other kinds of things that the database provides. And so that persistence model you saw, that's fully opt-in. Other teams around Microsoft achieve a similar kind of effect by using custom plugins. So they'll have a custom, let's say, Azure storage plugin, and then they can choose exactly how their grain state gets stored in Azure storage. The next thing I want to mention is distributed transactions. And this is a cool, very kind of unique feature in Orleans. You can actually inject transactional state into your grain. So imagine you want to build a bank and you want to have, say, 2 bank account grains and transfer some cash between them. So you might have a method, let's call it transfer, and transfer can call into one grain, deduct some funds, and then call into another grain and increment some funds. And you can make this all transactional so that even though those grains have their state stored in totally separate places, and they can actually even be separate databases altogether, Orleans can guarantee that this happens in a transactional manner, and you get strong isolation on that as well. And that's a pretty crazy kind of a feature, I think. So transactions can really simplify life for a lot of these kinds of applications. Like a bank account is probably the classic example of that, but there's other cases as well. And it helps you to avoid a lot of the kind of pitfalls that you'll get when trying to build big systems that need these sorts of features. Next is virtual streams. So you saw on the previous slide again that we were making method calls, asynchronous method calls, and that's the RPC paradigm. A lot of the time, though, a developer is going to want to decouple both sides of communication. And they also might want to decouple things temporally, like decouple them in time. So let's say I want to issue a request, and then I want to be sure that that does get processed, but I don't really mind if it happens a little bit later. And so Orleans has streams for this. And streams in Orleans are a pluggable abstraction. A lot of teams around Microsoft end up using Azure Event Hubs, which is a great choice because it scales well and is very reliable. But you can also use things like SQS, GCP, or even in memory if you want to do things like testing, or just fire and forget things that are not really that important. And these streams, they can have declarative bindings. So you can say that either you want to explicitly subscribe to a stream from a grain, or you can say, all right, well, I have a grain and I want these grains to subscribe to any stream with the namespace X. Or you might say, I want to subscribe grains to any stream where the namespace matches some predicate, like or regex or something like that. So it can actually run some code to decide whether or not it subscribes to that. So it's a very powerful kind of a thing. The next thing I want to talk about is deployment freedom. Now within Microsoft, we have teams running Orleans on Kubernetes, on Service Fabric, on Windows, on Linux, on Azure cloud platforms, the classic cloud services. So it's very unopinionated about where it runs. Runs pretty much anywhere the .NET can run. And outside the company, we see people running on AWS and GCP as well, and even on bare metal, on-prem or in the cloud on co-located machines. So it's very flexible. All right, so enough about the framework. How do we actually use it at Microsoft? Well, here are some of the products or services or even parts of the company that are using Orleans in some capacity. And we'll talk about a handful of them today. So we've seen services built on Orleans that are ranging from a single host all the way up to tens of thousands of cores. But a typical kind of a cluster size might be 5 to 40 nodes. And you obviously don't get too much resiliency from running on a single node because if it goes, well, it's gone. Now, there's a broad set of applications here. Some of them are in gaming, some of them are more geared towards the enterprise, and you see Azure Quantum and Azure Machine Learning down there that are more science-oriented. Some of these are very large, and Orleans is used somewhere in all of them. And within these services, we see different use cases like workflows, graph processing, analytics, stream processing, transactional workloads, and resource scheduling, just to name a few. The one thing that's common to all these use cases, or all these cases, is that state is naturally partitionable. So it maps very nicely to grains, and it can be more easily distributed across a cluster of machines. So for example, in the IoT case, you might have devices, or you might have users, sessions, purchase orders, workflow jobs. Those kinds of things are really readily distributable. And when designing grains, you need to think about the granularity you're working with. If you have a single grain that's involved with 50% of all of the requests, well, you're going to hit a wall when it comes to scalability. And conversely, if you have a request that needs to fan out to say 50 grains in order to get back an answer, that's going to add additional latency and it's going to limit your throughput. So that granularity is important. Now, to get a little more concrete, imagine you're building a chatter. Would you have a grain for every chat message? I would say no, probably not. But you might have a grain for a conversation between users and cache only the messages that you need in memory. That scales much better, and it's much better latency as well. Now, game studios use Azure PlayFab for building and operating their games. Many studios within Microsoft and outside rely on it for some massive titles. And PlayFab is much more than what I'm showing on this slide, but I want to mention these three cases using Orleans. And in the interest of time, we're going to talk about the first two in a little more detail. So let's dive into PlayFab's multiplayer server hosting. Now, PlayFab runs game servers for studios, and these servers are spread across the world to ensure that gamers get good pings. And up above all of these servers, is a control plane that orchestrates everything. And that control plane is built on Orleans. Now, the model that game developers see is that they have a tenant, let's say it's 343, and then they have a game, let's say it's Halo, and then a deployment, which is a specific configuration of that game that they want to run. And so then they'll configure multiplayer services to keep a pool of these servers running at any time so that players can join without having to wait too long for a server to spin up, for example. And the control plane's job is to make sure that there's always a sufficient number of VMs that are in a healthy, ready state with that game server loaded at any point in time. And as a matter of scale, we tend to see hundreds of thousands of VM cores running in PlayFab multiplayer servers at any point. So the control plane has grains that represent things like tenants and titles, deployments, VM pools, VM allocators, monitors, and even individual VMs. And VMs will send the status heartbeats up to the control plane, so the control plane can keep status updated locally and make decisions on it, and then it'll eventually pull VMs out of a pool to allocate them to a given game session. Now, Orleans clusters are very resilient, and they'll detect failed nodes automatically and recover from those failures. The gamers really dislike outages, so there are multiple control plane clusters hosted in different regions to ensure that if one region has a blip, then another one can take over. And clients calling into the control plane, well, they use HTTPS. And the control plane co-hosts the HTTP server within the same process as the Orleans silo, the Orleans server, and we do this using the .NET generic host feature. Now, by co-hosting the HTTP frontend with Orleans, the frontend can directly call local grains without needing to make network calls or do serialization round trips. But when it does need to cross the network boundary, by co-hosting them, it has access to knowledge of the current state of the cluster, so it can avoid going through additional gateways and instead call directly to the place that it needs, avoiding network hops and significantly improving performance as well as resiliency. So that was a recent change to the multiplayer server's control plane. Now, the HTTP server used to be separate from the Orleans server, and they changed to merge them together into one process and gain that performance. That didn't require changing the application code. It only required changing the hosting code. So when we set it up and we have this generic host, instead of just adding the HTTP server, we also add an Orleans silo in there. And by doing that, without changing the application code, we can merge these two things together and we get that performance optimization. And just as easily, you could separate those two things apart. So there's a nice amount of flexibility there. PlayFab's economy service allows game developers to process payments, manage virtual currencies, sell items, and guard against fraud. And so they have grains that represent accounts. And within those wallets, they have multiple currencies. So you can think of a currency as either an in-game item or something that's more traditional sort of a currency, like, for example, rubies in Minecraft Earth. And when dealing with real money, you often want to use transactions to make sure that you can avoid exploits and you can prevent unhappy players. Because if players are paying for something and they don't receive it, well, that causes agony. And the economy service uses Orleans distributed asset transactions for that. It's very similar to the bank account example, but they have a custom storage provider and it's built on Cosmos DB, and they use a currency per document in there. And they do that because it allows them to only modify the documents they need to modify when they need to modify them. They also have custom participant in the transaction, so they can monitor these transactions and output the lifecycle messages like commit, abort, and prepare, for example, into an Azure Event Hubs, and they do that in order to form an audit log. All right, so Halo is probably the most well-known application using Orleans, and multiple Halo titles have relied on Orleans-based services for a while. Multiple Gears of War or Gears titles are also running on Orleans, or at least their services are running on Orleans. And for the Halo case, they built services for tracking players in near real time, performing detailed analytics on the game matches, and also doing things like cheat detection, like detecting modified consoles or detecting griefers in the game. And they also have content management servers. And for the analytics part, they're using Orleans streamed on event hubs so they can reliably incorporate what happens in each match into a player's profile. And for Gears, the Coalition up in Vancouver, they also use Grains to create a lobby service. And other studios outside of Microsoft are also building lobby services on top of Orleans. You can see more details about the Halo case in some of Katie McCaffrey's talks, and I can link you to them. All right, we talked about a bunch of cases in Microsoft that are built around gaming, and those use cases, they can be applied elsewhere as well. But we want to talk about other cases around Microsoft. So for example, Azure IoT has built their digital twins offering on Orleans. And IoT is a good use case for Orleans because the Internet of Things, well, each of those things can be mapped very nicely into a grain. And so IoT digital twins allows users to create these graphs of their digital twins, these IoT devices. And instead of having a big soup of devices, they can create relations between these things. And so they create bidirectional links between the grains. And for reliability, they use reminders. And reminders in Orleans are a kind of a a durable timer. They're like cron jobs, but they're scoped to a grain. So they will, for example, set a reminder, and that reminder will ensure that even if a machine suddenly fails partway through this, it's okay because the reminder will fire again very soon. And then that process of creating this bidirectional link can complete in a reliable fashion. Now, Dynamics 365 fraud protection, it helps businesses to detect fraud in things like e-commerce or account usages or in bots. A good example of this would be the e-commerce case where you've got users and the users are doing things like making purchases. And those purchases will have, for example, payment information, shipping addresses, billing addresses, the IP address that the user used. And so they can run some analytics on these things and detect fraud in real time as it's happening on these grains. Other companies have also used Orleans for identity-based or user identity-based applications to great success. Now, Gigia is one example that was acquired by SAP. One thing that's interesting about the Dynamics case is they've actually got geo-distributed clusters. So they've got clusters in multiple locations around the world, and they've used some custom Orleans modifications to allow them to have certain types of grains be roaming between those clusters. So they're always accessible from anywhere, but they'll exist at most once in any of these clusters around the world. So you can do some really interesting things there. Now, the final case I want to talk about is Azure ML and Azure Quantum. So these things, in the interest of time, we'll keep them together. They're different, but they have a lot of similarities as well. And Azure ML runs a broad range of different services on Orleans. So this is just a selection of what they do. But as a whole, as a product, they allow you to design and train and then serve up models. Now, Azure Quantum allows users to submit quantum computing jobs, and then they get run on special hardware like simulators and things, so that you can run quantum computing experiments. In both cases, though, you have some special hardware and you want to maximize the use of it. So they build job scheduling systems on Orleans. And again, they're using those reminders to make sure that these things end up being nice and reliable. All right, that's all I wanted to show you today. So .NET, Orleans is built under the .NET Foundation. We build it openly on GitHub, so improvements and features are coming often. We have a warm and welcoming community up there on GitHub and in the Gitter channel, but we also try to be very open and approachable. So please feel free to contact us directly if you'd like. Thank you.
All right. Let me get the questions up and going. Oh, shared the wrong thing. Too many windows. So you can see that. So, all right. So one here for you, Ruben, is how is Orleans different than Service Fabric? I'm sure you guys get that question a lot.
Yeah. So Service Fabric and Orleans are actually quite different things. You saw that I mentioned that Orleans inside of Microsoft is often being run on Service Fabric. And for example, that multiplayer service case, they're running Orleans on top of Service Fabric. So Service Fabric is a few things, one of them being a hosting platform that will manage application rollouts and keep things reliable in terms of running your servers. And there's also an actor model inspired by Orleans that's built on top of that. So they have that actor component that's also running on there that's sort of tied to Service Fabric.
Perfect.
Hopefully that explains it.
Great. I was going to say we have another question from @UnicornBeast that asks, if a silo goes down, how can I ensure the data from the grains? I'm sure, how is the data not lost, right, as if something were to happen?
Yeah, that's a good question. So you will configure storage providers, and so your grains can have persistent state. They can either have state that's in memory, and in that case, you'll lose the state if it fails, which is okay for a lot of cases. But in the persistent case, you're writing your data back to storage every time you're modifying it. So you can use a variety of backends there.
Right. So at that point, essentially, it's up to you to essentially try to persist the data as the silo is running.
Yeah, that's right. So you'll persist it, and then Orleans will make sure that it gets loaded before your grain runs next time, in case there is a crash somewhere.
Awesome. That's great. So actually, the next one, it seems to be like a three-parter question. So I'm going to start with the first one, and we'll go through it. All right? Yeah. So the question is from Mazen Ezzedine, which is, does Orleans provide a guarantee on execution semantics exactly once processing? And so to roll through it, so the state is persisted in a remote storage cluster, and the state of computation of Orleans objects are not coupled for any persistence and impact.
Okay, so I think we should deal with the first question first. Does Orleans provide any guarantee on execution semantics?
Yes.
So exactly once processing, Orleans messages if you're using the RPC paradigm, you get at most once. So we're not going to retry your messages automatically for you. You can, of course, use something like Poly if you want to have retries. And there's a feature called call filters, and that also allows you to put some retry logic in there if you want. Now, you can achieve exactly once kind of semantics if you're careful about the way that the application is done. For example, if you're doing things on persistent streams, then you can checkpoint where you're up to, and you can store that information so that process only new messages and you don't process messages twice. And you can achieve, I usually call that effectively once processing rather than exactly once, because the result of it is only visible once. Right. In other cases, like, for example, in the commerce case that I mentioned with the digital economy, they want their transactions to be able to be executed once. But if the caller doesn't know that that happened and something failed somewhere along the line, or they're replaying some logs, they still want idempotency, right? And so they actually have a grain involved in some transactions that acts as an idempotency check. And so that says, okay, if I've already executed and this transaction is committed before, don't commit it again, just return the same result. So there's a few different ways you can achieve that effectively once processing.
Great. I was going to say, since we're out of time, if you go to Twitter, you can actually answer those questions.
Yeah.
Right. So if you go that, because like I said, it's a pretty long. It's like, and this, and what about this? It's a pretty good scenario. I was reading as you were going through your session. But anyway, thank you so much, Ruin, for taking the time to talk to us and show us about Orleans. It's a really great topic.
Sure.
Thank you, everybody. We'll be right back. We're going to get Cecil Phillips up and going here. So we will stay tuned.